get started on this. All right, share my screen. Okay. So first question is this. Again, hopefully you did your readings. That being said, I understand some of you might be in, oh, I'm freaking out about the exam mode and maybe didn't do your readings. But of course, if you did that, you have to make sure that you catch back up. And reading week is a perfect time to do that, right? Okay, so we're at about 2/3. This one's a pretty quick one. So again, I'm going to give you about 30 seconds here, then we'll finish it off. And I'm pretty happy with what I see. And stop. And we'll share the results. Okay, beautiful. Like 90% of you got B. B is the correct answer. If it wasn't B, we would be very worried, but it is. I realize I actually haven't set up my thing for these notes. So let's do that right now real quick. And I can't see because the stupid Zoom thing is in my way. So I can't actually see what I'm doing. There we go. All right, so to see why this is the case, again, we have the following. Remember, you have to be a solution. I know most of you got it, but let's just make sure that we're all on the same page, right? So this is question 1. And we had the system x plus 7y equals -5, 3x plus y equals 5, and 4x plus 2y equals 5. Okay, now remember, to be a solution, we have to, like, our point has to satisfy all 3 equations simultaneously, right? So a solution must satisfy all 3 equations at the same time. Right? That's critical. So if you start going through them, you'll see most of them actually don't even work for the first equation. So the first option was A, right? In this case, it was xy equals what? 1, 1. Yeah, that doesn't even work, right? If you plug that into the top equation, you'd get you get 1 plus 7. That's equal to 8, not equal to -5, right? So you immediately throw it away. If you tried B, so that's going to be 2, -1. Okay, it satisfies the first equation, right? You get 2 minus 7, that's -5. Second equation, 6 minus 1 is 5. Yep. And boom, 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 everything works. So that is definitely an answer. Now, it's actually possible. Oh, yeah, sorry, third equation is 6. Thank you. Now, it's actually possible that this could have multiple solutions. So we should probably just quickly sanity check that there isn't a second one, right? So the next one is 1, 2. Again, plug it into the first equation. It doesn't work. And the last one is 3, -4. Does that work? No way, right? If I plug it into the first equation, I get 3 minus 28. That's negative 25. So in fact, the only one which satisfies even the first equation, only B satisfies the first equation, but importantly, B actually satisfies all the three of them. Okay. Now, this was a sort of question. It's easy to check if you have a solution to a linear system. It's a different sort of story to find the solution if you're not given it, right? So in this case, you're able to easily verify that B is in fact the correct answer, but it's a different thing if you actually want to solve it. And that's part of what we're going to be doing. When we come back from the reading week, we're going to talk about how exactly do we actually solve these systems. And I think many of you have seen these sorts of things before, right? Where you take -3 times the first equation and add it to the second equation and, try and kill the x's and solve for y and these sorts of things. So you've probably seen that sort of stuff before, right? Okay, let's do this one then. So I very conveniently graphed for you these two equations as well, which will help a lot. Okay, so we're at about 2/3. Again, I'll give you about 30 seconds to finish it. Yeah, so I mean, a lot of, this is kind of like the intro stuff, right? So stuff's going to get harder. But let me kind of put it this way. There's lots of things in real life. Like right now, almost everything we do, variables are just like X and Y sorts of things. But there's lots of stuff in real life where you actually have, thousands of equations and thousands of unknowns, right? And you need to know how to be able to solve those things. Obviously, you wouldn't do it by hand, but you kind of need to know how to use a computer in order to solve those things, right? So yeah, it's very common to have things with thousands of equations and thousands of unknowns, and you're trying to solve those systems. Okay, so I'm going to end it. Let's see what's happening. Beautiful. Almost everyone said A, and yeah, absolutely, A is the correct answer. You know what? Actually, here what I'm going to do in order to make the presentation of this one's a little bit easier. I'm sorry, that might be a little bit loud on the mic, but I'm actually just going to like copy and paste this graph because I want it when I actually do the solution. What do you mean you can't cut from the, what are you lying Microsoft nonsense BS stupid thing? Just work. Literally the only reason why you're any good is that stuff's supposed to be easy. Thank you. If it doesn't work, what's even the point?
You just have to give it some time. That's all it is.
Yeah, do everything twice. Okay. Is it okay to use a graphical display calculator? Ali, let me actually explain a little bit about that later and how your term test 2 is actually going to work, because it's going to be a little bit crazy. All right, here's question 2. But so let me cover this one first, and then I'll answer that question. Okay, Ali? So if I forget, though, maybe give me a little reminder. All right, so let me just kind of quickly rewrite down what the system was. So the system, we had 2x plus y equals 5, and we had 3x minus 2y equals 4. Okay, and to my mind, I actually think that the red one is this equation. I'm pretty sure. Oh, I didn't get the y somehow. Okay, and then the blue one, I'm pretty sure, is this equation, like that. Okay, so stupid thing. So it's asking now, which of these 4 options can we add in order to still get a solution? And if nothing else, what we can immediately do is say, look, if these are the 2 graphs that we, everything on the red line satisfies the red equation, and everything on the blue line satisfies the blue equation. And so if we want both equations to be satisfied simultaneously, critically, it's going to be, there's one and only one solution, and it's this one right here, right? 2, 1. And if we check that, if we actually plug x equals 2 and y equals 1 into both of these equations, Curdy, exactly. If we plug those into both of these equations, we see, yeah, it does satisfy it. So first thing that we could do is we could just start plugging 2, 1 into our 4 options, right? And our 4 options were x plus y equals 1. Okay, boom, already done, right? That does work. So yeah, that's probably the right answer. And then we get 2x plus y equals 7. Does that work? No, it doesn't. C is x plus 3y equals 1. Okay, that doesn't seem to work either. And D is x minus y equals 2. Okay, so A is the only one that works. But the reason that we've done this problem like this is I want to show you something else, another way of thinking about it. X plus, sorry, what? X plus y equals 3? Oh, sorry, x plus y equals 3. Thank you. I'm clearly just having trouble today copying stuff down verbatim, right? I've done that now twice, but no, thank you. But so there's another way of thinking about it, which is, okay, Natalia, let me answer that question in a second. The other way that we could think about this is as the following. If we were to graph these 3 equations, what we also need is that those equations pass through the point 2, 1, right? So they have to pass through the point 2, 1. And so I'm going to let you worry about trying to graph B, C, and D. But if we graph A, we are going to get a right answer, because the graph of A is going to look like, oh man, I don't know why it squiggles. Is that my hand, or is that Microsoft? I'm going to say it's Microsoft. Okay. So apparently my hand is not steady enough to keep it from squiggling, but basically if you graph the line x plus y equals 3, you get this thing, and it also passes through this point 2, 1, right? So geometrically, we can visualize this. Now, in a direct message, I was asked, how would we solve this if we did not have a graph? The answer is we just have to solve the linear system, right? We'd have to find the value of x and y, which solves this. And we're going to learn techniques for how to do that later. Some of you probably know high school techniques to solve this, but we're going to learn better techniques later. And so if we didn't have the graph, that's unfortunately how we'd have to do it. But in this case, we did have the graph, right? If we wanted to graph it, would we make it y equals mx plus b? You could do it. And Ali, you'll have to explain what you mean by simultaneous. Or are you like wondering what I mean when I say simultaneous? So Curdy, you could, if you wanted to, write it as y equals mx plus b, but there's a cooler trick. And basically, yeah, well, I mean, if you solve the first 2 equations simultaneously, then yeah, in fact, you would get 2, 1 as an answer. So you wouldn't have to solve these 2 equations and the third, like you wouldn't want to plug the third equation in and solve it. What you would want to do instead is solve the first 2 equations and then see which of the third ones also had that as a solution, right? And that there's a chance that wouldn't work if you actually got infinitely many solutions from the first 2. But in any case, we're kind of getting ahead of ourselves, because when I say how many solutions does a system have, we're not there yet, right? So I don't want to get into this too much right now because this is not the objective that I'm trying to get from this, as much as I'm trying to show you the algebraic versus geometric idea behind how solutions work, right? Could I explain again? Sure. So again, we know that a solution to this is x, y equals 2, 1, and we can get that from the graph. And then so we just start plugging in 2, 1 into these equations until we get an equation which is satisfied. And that's how we figure it out. That was the first way. That's the algebraic way. The second way is to graph each of these equations and see which one of them passes through the black dot at 2, 1. Let's make that big, that black dot even bigger, is to graph these 4 equations and see which one of them passes through this point. And the answer is that only one of them actually works. Okay, so that was it for the direct message that asked me how to do it. And yeah, and if we had to solve it without the graph, that's not something that we've learned yet, but we will learn it later on. Okay, so does that make sense? With any remaining questions about that? Okay, cool. So let me do the next question, and I'll explain kind of Ali's thing. Okay, so here's a question: how many solutions does this have? Let me restart the polls, and then I will answer the question about graphing calculators. So the rule, and this is going to matter very much for the next term test, not so much for this term test, but what you may have noticed if you've read the test instructions for term test 1, you may have noticed that we said, yeah, you can use a calculator. In fact, you can use any calculator that you want. You can use a graphing calculator. You can use a finance calculator. You can use Wolfram Alpha. You can use Desmos. You can use Symbolab. You can use whatever you want. We don't care. So you can use anything. Now, when it comes to doing linear algebra, some calculators are better than others. And so much so that we have, as a group of instructors, we have decided on a piece of software that we are going to strongly recommend. And that software is called Octave. Now, Octave, we've included, if you go to the syllabus and you go under the other section, the very last tab, there's something there called the Octave cheat sheet. And it will tell you the most common commands that we will use in this class in order to solve linear systems. You 100% will be able to use that software in order to help you solve linear systems. And in fact, we expect you to use some sort of software. It is the one benefit really of giving you an online exam, is that we can now give you really big linear systems, like 6x6, 7x7, 8x8 linear systems. And because you're allowed to use a calculator to solve it, we can go, yeah, we can give you big systems and it's okay. So I'm not going to show you Octave quite yet. It's something that we will do talk about a little bit more when we actually need to start using it. The first equation doesn't make sense. What do you mean it doesn't make sense? But anyway, so well, Ahmed, while you're answering that, when we need to start using Octave, I will show you how to use Octave. Okay, and I'm not going to just throw you into the deep end. I will show you how to use it, and you will all, I think, go. I was kind of surprised by this. Let me give you a story. So this class, I think most of you are probably, doing commerce management sort of stuff, but there was a while when a lot of econ students used to take this course as well. So I always still talk with the econ people to see what it is that, they need from this course. And when I asked the econ people, I said, do you want me to show them how to do any modeling? Do you want me to show them how to use a computer to model things? And econ was like, no, we only do theory in undergraduate. The grad school is when they would start to do models. And this, first of all, this floored me. It's economics is something that is model based. Why are you doing only theory in undergrad, right? That's madness to me. I don't,
I could tell you experience as well. I went through the economics route as well. Every chapter starts with a page of assumptions that don't make sense, right? So every time you read all the theories afterwards, or all the models, you can call them, they're not based on real life because they have a page of assumptions that's based out of. So.
Right. Yeah. So, okay. I'm perfect. So this is what econ told me. And so generally I've stayed away from showing students computers. And my assumption was always that if I showed the 133 students how to use a computer to solve these problems, they would get angry and upset. And then last year we said, listen, whatever, we're going to do it. So I showed last year's 133 students how to do it. And in my experience, the consensus was generally, holy crap, this is so much easier. Like, this is so awesome that we can use a calculator to do this. It's not as simple as like a calculator you're all thinking of, where you push buttons. You actually have to type some stuff, but it's so easy. It's crazy. And so they actually really seem to enjoy it. So that is something that I've kind of baked into the course now, and I'm trying to figure out how I'm going to do it when we go back to in person, but I'll figure that out. Okay, so this one is going a little bit slower, but we are at 70%, so I'm going to give you about 30 more seconds. Does econ do graphing too, like opportunity cost and all that? Not 100%. I mean, there's graphs, right? So for sure there's graphs, but they're all linear. In economics, everything is linear. Everything's a straight line. Okay, so we are decidedly significantly more conflicted about this than any of the previous questions. Okay, can anyone give me one solution? Does anyone have just one? Okay, yeah, 1, -3. All right, sweet. So a lot of people did that. Can anyone give me another one? So we have 7x plus 2y equals 1. We have -14. That's a 4. 14x minus 4y equals -2. Okay, so some people said 1, -3. I've got one here that's 3, -10. Does that one work? 21 and 20. Yeah, it seems to work. Right. 1. Okay, does anyone have another one? 0.5. Yeah. Right. So I think most people are getting that by guess and check, but Tina is now providing kind of the interesting idea and the interesting perspective, which is that the second equation is just -2 times the first, right? So really what we noticed here, let's maybe name these equations. I'm going to call this equation 1. I'm going to call this equation 2. So notice that, oh, pen stopped working. Yeah, but exactly. These lines are parallel, right? Seif has said this. Tina has now said this too. So these lines are not only parallel, they're more than parallel, because if they were parallel but didn't touch each other, then there would be no solutions. They are in fact the same line. Exactly. So notice that these are the same line. Since equation 2 is -2 times equation 1, right? So they're in fact the same line, and which means that they're actually, when you say, where do these two lines overlap? The answer is in infinitely many places, right? Exactly. They're overlapping coincident lines. So that in fact, there are infinitely many solutions. Okay, so now here's an interesting question though. How many solutions can a linear system have? What are all of the options in general? Can a linear system have one solution, exactly one solution? Somebody tell me. Okay, we've got some yeses. Can a linear system have no solutions? Okay, right? That's what happens when the lines are parallel, right? So the lines are parallel and don't overlap. There's no solutions because a solution is wherever those lines cross. They can have one solution because if they cross, they're going to cross at exactly one point. And can they have exactly two solutions? Okay, the answer is no, because it is impossible for two lines to cross in exactly two places, right? Like think about it geometrically. If you were to graph two lines, if they cross each other, they cross each other once and they never cross each other again, right? But Brandon, if you have a parabola, then it's not a linear system anymore, right? Linear means that they have to be lines. That's what the LIN part of like the I, that's what linear means, right? Is that they're lines. So yes, if you had a parabola, you're absolutely right. There could be two solutions, but for linear systems, everything is always of the form, right? A1, x1 plus a2, x2. And these are all linear things, right? These are lines. And it's a little bit hard to visualize, but the same thing is true in 3 dimensions as well. If you have planes, planes can either overlap nowhere, they can overlap, if you have enough planes, if you have 3 planes, they can overlap in a single point, or they overlap in infinitely many places. It's impossible for them to overlap in exactly 2. We know it's infinite because if you were to graph both these lines, I mean, I don't really want to graph them. What is it? It's 7x plus 2y, so it's y is equal to 1/2 minus 7/2 x, right? That's the equation. So if you were to actually graph them, what is it going to look like? So 1/2 and then a negative slope. So the first line looks like that. The second line all is the exact same line. And the solutions to the system are everywhere where the lines overlap, where all the lines exactly meet. And in this case, the 2 lines overlap in exactly the same places. So there's actually infinitely many solutions. Or the way you could think about this is the second equation doesn't add anything that the first equation didn't already have. And so every point on this line is a solution. Okay, is there a trick to know if 2 lines are overlapping? I mean, actually, the way that we're going to do this is we're going to solve the linear system. And there's a way of determining from a linear system how many solutions there are, whether there's no solutions, 1 solution, or infinitely many. And in fact, the thing that's interesting stops becoming whether it's 0, 1, or infinitely many. But the thing that becomes interesting is how many infinitely many solutions are there, right? And what I mean by this is if you think about 3 dimensions, for example, let me see if I can do this. So the equation of ax plus by plus cz equals d in 3 dimensions forms a plane, right? It's like a sheet of paper. Now, 2 planes can overlap. They can either never overlap because they're like parallel, right? In which case that's no solutions. If you have 3 planes, you actually need 3 planes, but if you have 3 planes, they can actually overlap in a single point. That's hard for me to do. I don't have 3 hands. Or they can overlap each other perfectly and give you a 2-dimensional space of solutions. Or if they kind of cross each other, you see that these 2 things intersect in a line where the two pieces of paper meet each other, right? They meet in a line. So the line is called a 1-parameter solution set. The plane is a 2-parameter solution set. Okay, so the number of parameters of our solution set is going to then kind of become the interesting thing. And it says that we can break down the case of having infinitely many solutions into different cases depending on how many parameters we need in order to write out the system. Okay, does that kind of make sense? Again, it's getting a little bit ahead of ourselves, but a system can either have 0, 1, or infinitely many solutions, but we're going to break down the infinitely many solutions case in the future and analyze it a little bit deeper. Can I solve it algebraically? I mean, so here's the thing. If you were to solve this system 7x plus 2y equals 1, when you reduce it, you would just get this because the second equation is the first equation, right? So solving it algebraically just completely removes the second equation. Then you would say, well, how many solutions are there to this system? And the answer is, yeah, there's infinitely many, right? Like for any value of x you give me, I can find a value of y which solves this system. And again, that just corresponds to being a solution is every point on the line that I drew in the top right-hand corner. Okay, so that's what's going on there. Okay, so up until now, things have been fairly conceptual. let's maybe do a little bit of computation. Nothing too bad. All right, let's do this one. And again, everyone, don't worry about solving the systems right now. I am eventually going to show you how to actually solve these, right? But right now we're just kind of focusing on conceptually understanding what these things are, what it means to be a solution, and those sorts of things. Okay, but we'll solve them eventually. You'll see it. Well, Brandon, to an extent, you'll actually see it. Like I will show you where the motivation for matrices came up with. The mathematician who really did most of the stuff, though, was Grassmann. And most people kind of ridiculed him, and he died, in obscurity. And then it wasn't until we dug up his writings much later that we realized dude had it right the whole time. And so there's a couple things in math we actually name after him, notably the Grassmannian. But yeah, I'll show you when we get there how the concept of a matrix came up and why it's the correct thing. To really get into it, we need to understand functions between vector spaces, and those things are called linear transformations. We won't get that far into linear algebra, but that is kind of where things come from. That is the idea. Okay, we're actually at 80%. I stopped paying attention. So I'm gonna give you 20 seconds. Get your last minute votes in. All right, let's take a look. Yeah, overwhelmingly A, phenomenal A is the correct answer. All right, everyone's crushing it, right? So question 4. So we're told, what are we told? X is A, B, B, A. And Y is this thing, 0, negative A, B, 0. And we want 4x minus y, right? We want to figure out what that is. So we're going to do 4 times a, b, b, a minus 0, negative a, b, 0, like that. Guessing, whatever. Okay, so now when we multiply a matrix by a number, we just multiply every single element inside of the matrix by that number. All right, so we have 4a, 4b, 4b, 4a minus this thing. And now, because the matrices are the same size, and if they're different sizes, you can't add them, but because they are of the same size, we can just add them component by component. So we're going to get 4a minus 0, 4b minus negative a, 4b minus b, 4a minus 0. And so if we work that out, 4a, 4b plus a, 3b, and 4a. And that should be number A, or option A. Okay. So nothing too complicated there, right? If you add two matrices of the same size, you just add them component by component. And if you multiply it by a number, you just multiply that number into every single component of the matrix, right? That's how these things work. All right, so it's not, hopefully it's not too bad. Is there any questions about that? I started right away with the third step. Yeah, I mean, like, it's when I do this, I go straight to the answer, right? And so that's okay. If they're different sizes, you just can't add them, right? You just legitimately say that this question does not make sense. It's not possible to add two matrices of different sizes, right? So that's how you deal with that if they're different. All right, this one's not too bad, right? But no amount of computation will save you. So you have to know what the question is asking you. I don't think we'll need much time here. There's nothing to compute. Okay, so I'm going to give you about 30 more seconds. There's no computation here, right? So this one shouldn't take too long because you either just know what M13 is or you don't. Oshin, yeah, not even a scientific calculator. I'm going to show you how to use a computer to do it, which is way better. Okay. We are unfortunately a little bit split on this, and okay, A is not, all right, what is M3? What row, what column? The last one. Yeah, no, but what I'm saying is like 1, 3. When I say M sub 1, 3, what does the 1 mean? Row 1, column 3, right? Exactly, row 1, column 3. Okay, so we've got this matrix, and here's always the problem when you do linear algebra is writing down matrices is a big pain in the butt because they're quite big, right? So we've got M is 1, 1, 4, negative 1, 0, 1, 0, negative 1, 1. Okay, so M1, 3, if I write this down, this is the row, and this is the column. Right? So I'm going to look at row 1. Here's row 1, row 2, row 3, column 1, column 2. Maybe let me call that C1, C2, C3, row 1, row 2, row 3. So I'm going to look at row 1, column 3. Yeah, there it is. There's the answer. The answer is 4. Okay, make sense? Right, and it's always, and you have to remember that order though, okay? It's row first, row is the first number, column is the second one, always. Okay, you don't want to get them backwards. that will lead to a mess, a nightmare. So it's row first, then column always, okay? Row and column. All right, let's do one more before our time's up, and then I'm certain my office hours will just be answering financial math questions, but let's do this one. So again, I don't think, right, there's nothing to compute here, just do you know what this augmented matrix means? Okay, so this is another you know it or you don't. So I'm going to give you 30 more seconds. Okay. And all right, so we're answering towards A, but a couple people are in the B, and then we've got some stragglers in C and D as well. A is the correct answer. It is 2 equations and 3 unknowns. And let's see why. So for question, this is question 6. So we have this augmented matrix. I'm going to actually write down the linear system for you, because one of the things that we have, which is very much an objective, is you need to be able to translate between a linear system and the augmented matrix. Okay, so in this case, here's the augmented matrix. What is its corresponding linear system? So it's going to be x plus 2z is equal to 4, 2x plus 9y plus z is equal to 1. Right? So basically that augmented portion, the vertical line tells you where the equal sign goes. And then everything on the left is the coefficients of the variables. And then each row is an equation. So what do we have here? We have 2 equations. Right? And we've got 3 variables, so 3 unknowns. All right, so that was option A, like that. Okay, makes sense? Okay. Now I think that's probably a good place to stop for today. No point in getting too far into it. So I think we can call lecture there. And then again, if you want to take off, you absolutely can. Otherwise, we'll transition into office hours here. Because I'm certain that there are lots of like financial math questions and segment questions you'll have for me. Maybe just give me, let's say 5 minutes here, just again, kind of collect myself, refill my water and all that sort of stuff. Okay. And Aziz, are you taking off?
I have my tutorial starting in 2 minutes.
Yeah, for sure. Okay.
Okay.
Yeah, so everyone just get your questions ready. Give me about 5 minutes. I'm going to come back and then I'll answer all of your questions, everyone. Okay, so I'll see you in a bit.